Hello everyone, welcome to COMP382. In this video we are going to talk about the equivalency of finite automata and regular expressions. So we have already mentioned that regular expressions are just another notation to represent regular languages. It means that every regular language can be represented by a regular expression, and every regular expression is representing a valid regular language. So to prove that, we wanted to actually prove that regular expressions are equivalent to finite automata, right? Finite automata was another way to represent a regular language. So here we have to actually prove that every finite state is equivalent to a regular expression. It means that for every finite state there is a regular expression, and for every regular expression there is a finite state. So basically, because we know that NFA, DFA, and epsilon NFA, all of them are equivalent, we have already proved them, right? They can be converted to each other. So the two theorems that we are going to prove is, one of them is converting DFA to regular expression, which actually shows that, so if you have a DFA, you can create a regular expression for that. And the other part is using epsilon NFA, that say if you have a regular expression, you can create an epsilon NFA for that. Both of these two proofs are going to be constructive proofs, so not only we will prove it, I will actually just show you that how we can convert a DFA to a regular expression, how we can convert a regular expression to an epsilon NFA. So the first one that we prove is going to be the theorem 2. It actually makes more sense. Then I will actually talk about the theorem 1. So the theorem 2 is about converting a regular expression to an epsilon NFA. That shows that both of them are going to represent the same language. This proof is going to be constructive, and it's kind of actually inductive as well, because the regular expression, remember we defined a recursive definition for regular expressions. That recursive definition is going to help us here. We are going to go over the recursive definition of regular expression and show you that how we can create an equivalent epsilon NFA for any regular expression. So the first thing is that we will start with the base cases in the definition of regular expressions. Remember, in the base cases of the definition of regular expression, we had three base regular expression: empty set, epsilon, and every single symbol in the alphabet. So for each of these cases, they are all valid regular expression, right? I can create an epsilon NFA for each one. So this is an epsilon NFA, or actually in general this is a finite state equivalent to empty set. This finite state doesn't actually accept any string, right? So it's going to accept the set of empty strings. Epsilon is going to be representing the set of strings which is only containing epsilon. So this finite is representing that, right? You can see that there is no transition. There is only one state, that is a starting state, and it is also a final state. So you will only accept epsilon in this finite state, nothing else. And the other one is some finite state that accept a single symbol from the alphabet. So you can see that I have created finite state for that. Q0 that has one transition with label A that goes to a final state, and this finite state is going to just accept the single string A, nothing else. So if for every symbol from the alphabet I can create a finite state to accept that string. Okay, so we covered the base cases. Now we are going to go through those three operators that we defined for the regular expressions in the recursive part of the definition. First, the first actually operator was, I believe it was union, right? Okay, so now assume that I have two regular expressions, R and S, right? So so far we can assume that, okay, R and S are going to be used to create a larger regular expression, R plus S, right? So for each R and S, I can assume that we can create a finite, we can create a epsilon NFA for them. So this is a finite state for R, this is a finite state for S, right? So you can assume that I'm representing this one with ER, the other one with ES. There is going to be a final state here, there is going to be some final state here. Okay, I can create an epsilon NFA to represent the union of all strings which are represented by R and S, which means that all strings that are accepted here and all strings which are accepted here. I can simply create an epsilon NFA for that. How? So I can just added a new starting state, and then just move from the starting state to the starting state of this ER, and move from this starting state to the starting state of ES. So this is actually this one, and this one is this one, and I can actually move with epsilon transitions, right? So these epsilon transitions are actually helping me. I can actually create another final state, QF, and move from those final state of these two sets, these two epsilon NFA to this final state. So you can see that from the starting state, you can either move from here and reach to a final state, or you can either go from this way to reach to a final state. So all the strings which are accepted by this final state and all the strings which are accepted by this finite state, all of them are going to be accepted by the bigger finite state that we have created here. Okay, so this is going to represent R plus S. Here is actually the nicer picture for that. Definitely better than my handwriting. Okay, so we covered the first operator. The second operator was concatenation. So we wanted to create an epsilon NFA that accepts all the strings represented by the concatenation of R and S. If I have a finite state for R, and if I have a finite state for S, I can create a larger finite state by just actually putting this finite state here, moving from the final state of R using an epsilon transition to the starting state of S. Okay, so it's just like if you wanted to reach to the final state, you need to start from the starting state of R. You have to actually reach to the final state here. You can see that this one is not final state anymore, but this was the previous final state of the ER. Okay, and then if you wanted to reach to the actual final state, you have to actually move to the starting state of ES and reach to this final state. So basically you have to reach to the final state here, and then you have to go through some path to reach to the final state here. So all of the strings represented here and all of the strings represented here, all of the strings represented here needs to concatenate it to the one string represented by the other final states to be in the to be accepted. So it's going to represent the concatenation. And the killing closure, it means that you are going to have arbitrary number of r, right, including epsilon. So what I'm doing here is that this is the finite state represented the r, okay, so I don't have s anymore. So this is a finite state representing r. What I'm doing here is that I would add a couple of epsilon transitions. One transition that goes from the final state to the starting state. So in this way you can actually go arbitrary number of times. So arbitrary number of times you can go from a starting state to the final state, then come back and again go here, come back and again go here. And so I will create a new final state here, just at the end using an epsilon and fa, you move back. And because r star is going to include epsilon, so I need to move another epsilon transition that allows to accept epsilon here, not only all the arbitrary number of r, but also epsilon is going to be a part of the string. So here you can actually see that we can create for all of the operators of the binary strings and all the base cases, all of the operators of the regular expressions and all the base cases of the regular expression, we could create an equivalent finite state. So it actually just proved that if you have a regular expression, you can convert it to an epsilon and fa. Let me actually show it to you over an example. If it is not clear, you will actually just see that what would happen. So just assume that I have a regular expression like this. If I wanted to use that method to create an epsilon and fa for that, I can actually think about it in this way. That, okay, 1 is a regular expression, right? So this one can be represented using an NFA. 0 is also an epsilon. 0 is also a valid regular expression, a base regular expression. I can convert a regular expression, an epsilon NFA for each of these. Let's actually do them. So this is a regular expression that represents 1, right? This is a finite state, sorry. This is a finite state that represents 0. Then I can actually apply the union operator to create an NFA that represents the union of 0 and 1. This is the way that we actually added that. Add 2 epsilon transition, right? Add a new starting state, 2 epsilon transitions to go to the previous 2 starting state. And from the final states, you move to actually a new final state. So this is going to represent the union of 0 and 1. And then I can actually apply the closure operator. Okay, I just create a bigger finite state for other part of the regular expression. So to create that, what I'm doing here is just, remember, add some epsilon transition from the previous final state, right? It was a previous final state going to the starting state, and then also added an epsilon transition. This is the new final state and this is the new starting state. Okay, so now so far I have created this part. So I can create another regular expression, another epsilon NFA to represent 0, and which is going to be this one. And then I can concatenate these two. I can concatenate this one and this one to get the bigger regular expression. You can see that for that concatenation, I just need to add an epsilon transition from the final state here to the starting state here, so that if any string wanted to be accepted, it actually needs to go through this path. It should has a 0 and then should go through the path to reach to this final state. So this is going to be the equivalent epsilon NFA for this regular expression. Of course, you can see that this approach is not a good approach to convert a regular expression to a finite state. If you know, in your assignments or in your exam or whatever, I ask you to create the equivalent finite state to a regular expression, it's better to just first examine what is the regular expression representing and directly create a finite state for that. So the regular expression here that we have is going to represent all binary strings that starts with a 0. So I can actually say that I can create a finite state for this language. So this is going to be starting with a 0, go to a final state and have arbitrary number of 0 and 1s. So this is going to be, you see, you can create a finite state as simple as this for this language. But this approach just show you that for any regular expression, you can convert it to a epsilon NFA, and you can just think about it in this way, that I can even write a computer program. I can write a program that you just give it a regular expression and your program create an epsilon NFA for this. So it is a mechanical approach. It just shows you that what is the algorithm to convert a regular expression to a finite state. Let me actually show you another example. Here I have again a regular expression. I can use that approach to create an epsilon NFA for this. So you can, let's first create a epsilon NFA for this part, and for this part, then we will actually just concatenate all of them. So this is going to represent 0 plus 1 killing closure, which is basically say that arbitrary binary string, right? This is this component, we have seen it before here, right? This is exactly here that we had here. So this component and this component are the same, and the middle component is just the concatenation of 0 and 1, put the same component at the end, and so this is going to be the full epsilon NFA for this regular expression. Although this is clear that what does this regular expression represent, you should think about it in this way, that all binary strings that has the pattern 0, 1. You care about this pattern 0, 1, and you are actually allowing to have any number of zeros or ones at the beginning or at the end of that. So of course I can create a finite state for that, and that finite state is going to be, I can create an NFA for this, like this, okay, 0, 1, and 0, 1, and then 0, 1. This is going to be an accepting NFA for this. Or you can actually create a DFA for that as well. So you can create a DFA like this. 0, 1, it goes to an accepting state, right? And here if you see a 0, again you will stay here until you see a 1, that actually this pattern would complete and you reach here. So this is a DFA, and this is an NFA for the same string, the same regular expression. Here I have 2 more examples that I will leave them as an exercise for you. So when you are actually converting them to epsilon NFA, first try to actually use that mechanical approach that I showed you, that proof that I showed you. Then think about the strings, the regular expressions, and think that what does this regular expression represent? Create a simpler NFA for that. Okay, now the second part of the proof. The second part of the proof was the theorem 1 that says for any DFA we can create a regular expression for that. So actually before I give you the complete proof, I wanted to give you the idea that what is all this proof is about. So if you have a DFA, DFA is going to actually represent what strings are going to be accepted, right? What strings are going to be a part of the language. So all of those strings will start from the starting state and will end up to an accepting state. So it's just like if you have a DFA, you should think about it in this way, that if a string wanted to be accepted, it should start from the starting state and it should end up to the accepting state. So I'm looking for all the paths, okay, that started from the starting states and end up to an accepting state. All those paths, if I can convert them to a regular expression, that will be, representing all the strings which are in this language. Okay, so this is a very simple case. Let me actually show that what we have in this example. So here the first thing that I can do is that just converting all the transitions in the DFA to a regular expression. So the transition that I have here is 1. You see that this transition is going over the same state, right? So, okay, I can say that this transition will be represented using a regular expression, and that regular expression is going to be 1. Here I have 0, so I have a regular expression for this one, which is going to be 0. I have another 0. This is going to be a regular expression 0. This one is 1, so it's going to be a regular expression, which is going to be 1. Here you are allowing 2 transitions, both of them going to the same set, to the same state. So here I will represent this one as 0 plus 1. So, right, so when you have more than one transition over the same state or over the same transition, anyway, you just show it as a union, okay, because both 0 and 1 are going to actually move you to Q2. So at the end, when you are actually just wanted to convert them, you can see that this transitions over Q0, they are going to the same state, right? So you can have arbitrary number of this transition. You can go over this transition or not, right? So in general, you can have 0, 1, 2, 3, or arbitrary number of transitions. So this one can be converted to a closure over 1. This one you have to keep it. So this is going to be only 0. This one, again, this is a transition that goes to the node itself. So you are going to have a clean closure. You can have arbitrary number of zeros here, arbitrary number, either 0 number of zeros or any number of zeros that you want, okay? So this one, you have to have it, so you keep this one. And at the end here, you have 0 or 1, and you can have arbitrary number of them. So I would actually just put that 0 plus 1 over the closure. So wherever you have actually the transition over the same state, whatever is the label of the transition, put a closure over that. So in total, the final path that I wanted to create is going to be the concatenation of all of these regular expressions. So the final regular expression is going to be 1 star 0, 0 star 1, 0 plus 1 star. It actually shows me the path that started from Q0 and end up to a final state. So this is the idea, but of course this was a very simple finite state. I'm going to show you how you can convert any finite state to a regular expression. But I just wanted to show you that what is the idea. We just wanted to label all different paths that started from Q0 and reached to a final state. So the thing is, you can have a very complicated finite state, right? With arbitrary number of states. Not arbitrary, with finite number of states. But the number of states can be a lot. So you can have any number of finite states with any number of final states. right? And in between there can be actually multiple paths, for example, something like this. So how can I check all of the paths starting from the starting states and up to the final states, right? So one approach, I mean the approach that we are going to follow is state removal. In fact, I mean I shouldn't actually remove that. In fact, what I'm going to do here is that I wanted to simplify the DFA by removing the state, but still keep all of those, the information of the paths. So the thing is, I wanted to keep removing the states. For example, I wanted to remove this state to simplify the final state. But of course, when I'm removing this state, I should make sure that I don't lose any information. So if I remove a state like this and intermediate state like this, I wanted to add a path, a direct path that actually just preserve all the information here that I have. You can see that from this state you can reach to this one and this one through this state. So if I'm removing this state, I should actually create some other transitions to actually show, preserve all the paths that this state is giving me. And what are going to be the label of these states? The label of this transitions is going to be, for example, the concatenation of whatever you have here and whatever you have here. So that's going to be the concatenation of those two, whatever are those information. Or for example, the information, the transition, the label of this path is going to be, this transition is going to be, so whatever you have there concatenated to whatever you had here. Okay, so this is the idea. Now I'm going to show you the general case, then we will see some example. Okay, so here this is the situation that I have. I am interested in removing the state S. So this state is going to be removed, right? But this state can be, a state that helps to to reach from any of the states from Q1 to QK to these states P1 to PM. We can see that this is a completely general case. S is in fact just can be converting, it can be actually, just like S is a bridge that helps all of these states to reach to, for example, in different states here. Okay, so by removing S, you have to preserve all those possible paths that started from one of the states here and ends to one of the states here. Okay, and it is also possible that already there are some paths, for example, there are some transition from Q1 to, for example, P1, or from Q1 to all of these states here. So I just wanted to show you that what would happen in this case. So all of these labels like Q1, P1, R11, R1M, all of them are going to be the label of the transition. So they are going to be some regular expressions, right? For example, if I remove S, the path that goes from, let me actually just clean up a little bit here. If I remove S, okay, this transition from Q1 to P1 should be updated by this fact that, okay, either I can reach from Q1 to P1 using this label, so keep that, or I can reach from Q1 to P1 through S. If I reach from Q1 to P1 through S, what is the label? The label is going to be Q1, arbitrary number of S, and P1. So that is going to be Q1, arbitrary number of S, P1. let me actually show this one as a little p. So this is a state, this is a state. This was the previous label of the transition, and this is the new label. This is additional label actually to shows this path. I should get the union between these two to say that, okay, from Q1 you can reach to P1 either using this label or using this label. Okay, so I put the union between them. So this is the idea for all of these possible paths from Q1 to P2 to P3, for all of these to until PM. So you just update all of these paths with just the union of the previous label and this new label that will be created, which is going to be the path from Q1 to S, arbitrary number of S if there is any, right? And then the path from S to P1. So the final actually result is going to be represented in this way. These are just the union of all of those, the previous path, the previous transition, and the other path which actually went through S. Okay, so in this way, I can safely remove S. You see that in this new DFA, I don't have S. So the whole idea is that I'm just going to remove all of the states one by one and simplify the DFA so that at the end, you would end up to only one final state and one starting state, so the path will be clear. So before we actually reaching to that, let me actually show you some example. So we wanted to simplify this DFA by removing the state Q. How we can actually simplify that? So I should actually just say that, okay, from P, I can reach to R through Q, right? There is no previous actually direct transition from P to R. So it's just like you can think of it as there is a transition, but the label of that was actually empty, which basically means that there is no path, right? You can not reach from P to R, but you can think of it as the previous path was empty, so the union of empty and anything that's going to be that one. So it's just like you don't think about this path at all. So by removing Q, you are losing that path from P to R. So you have to create a new transition from P to R. And what is going to be the path? The path is going to be E, arbitrary number of G, and then concatenated to H. So this is going to be E, G star, H. What else I'm going to lose if I remove the state Q? You can see that one more thing that I can lose here is that the state P, you can actually start from state P, go to Q, and come back to P. Okay, so you should also preserve this information. So you go from P to Q and come back to P. So that transition that you need to put is the transition over P. And what is going to be the label? The label is going to be E, arbitrary number of G, and then F. So E, arbitrary number of G, and F. Similar to that, you can go start from R, go to Q, and then come back to R. So I need to add another transition that goes from R to R, and the label is going to be I, arbitrary number of G, and H. So here I can safely remove Q. The new final state is going to look like, okay, I just forgot that, going from R to P as well. Okay, how you can reach from R to P? You should actually see I, arbitrary number of G, and then F. I, arbitrary number of G, and then F. So this is going to be the final finite state by removing the state Q. Okay, so now that we know how to remove one state, okay, the whole idea is that we try to keep removing all the intermediate states. What would happen if I have more than one final state? If you have more than one final state, you actually treat each one separately. You keep, each time you actually just consider one of the final state as final state, and you just consider the rest of final state to be intermediate states. Remove all the intermediate states until you end up to only one starting state and one final state. Okay, so you can actually reach to two situations, either this one that the final state is distinct, is different than the starting state, or you can reach to this state that the starting state is also an accepting state. If the starting state is an accepting state, you can actually reach to a situation like this, right? If the final state is different than the starting state, the situation is going to be this. If you reach to either of these points, we can actually write down a regular expression. There is no more state to remove. In fact, we try to remove all the intermediate states except the starting state and the final state. When you reach to this point, I can actually write a regular expression for that. So consider this one. I mean, this one is simpler, right? So what is going to be the regular expression for this case? It's just like you are at accepting state, and you can have arbitrary number of the transition R. So basically this one is going to be whatever is R, just put the closure over that. So the final regular expression for this situation is going to be this. This one is a little bit more complicated. So what's going to be the regular expression equivalent to this finite state? If you reach to a situation like this, what you can do is that think about it in this way, that I wanted to represent all the paths that starts from this starting state and end up to accepting state. So you can have arbitrary number of R, right? I actually lose the states. You can have arbitrary number of R's here. You can have this path that actually go to the final states, and then you can have arbitrary number of U at the end of that as well. This is one path, but the thing is, you can actually, after going through this path, you can come back to the starting states and actually repeat this. So the final regular expression that I would write for that is going to be this one. That, I mean, it actually has been simplified. This part is this repetition that you can have. You can go here, see arbitrary number of U and come back to the starting states, right? So this is actually representing that you go to the final state, come back to the starting state, right? So this represents that, and R is representing actually if you just stay at the starting state. So you can have the union, the combination of these two to stay at the starting state, and you can have arbitrary number of this combination. So I put the star over that, and then at the end, if you wanted to reach to the final states, you have to go through at least one transition of S, and then you can have arbitrary number of U at the end. So this is going to be the final regular expression that you just need to memorize for this. Although it might actually look a little bit complicated, but in practice, when you see the examples, it's going to be much easier, much simpler for you to convert your finite state to the equivalent regular expression. So now the last question is that what would happen if you have more than one final state? just keep each of final state separately. For each final state, try to remove all the intermediate state and consider the rest of the state, all the other states to be intermediate states. Remove all of the other intermediate states. When you reach to a situation like this or this, write down the regular expression, and for each of the final state do the same, and at the end get the union of all of those regular expression that you created for each of the final states. Let me just show it to you over some example. Okay, this was the very first example that we saw. I'm going to show you how to remove the states. Here I have only one final state, right? That's going to be easy. I wanted to remove all the intermediate states. So to remove Q1, what I need to do is to just preserve all the paths that went through Q1. The only path that went through Q1 is the path from Q0 to Q2. So I can safely remove Q2 by adding a transition with, from Q0 to Q2 with the label 0, 0 star, right? This is arbitrary number of zeros, and 1. So, okay, the first step is that just convert everything to regular expression. So this one is going to be a regular expression. Then you remove this state, and you actually added a transition from Q0 to Q2. So now we reach to that exactly this situation, right? I don't have this transition, so instead of T, you can put empty here. So I'm going to just follow that formula that I had. Okay, this was the formula that we had, right? It's just like T is going to be empty. There is no path from Q2 to Q0, so T is going to be empty. So when T is empty, remember anything concatenating to empty is going to be empty. R concatenated to empty is going to be empty. So this part will be completely removed. This part is going to be empty. The union of R and MT is going to be R. So at the end, the only actually regular expression that remains is going to be R, S, U, R star S, U. So that's going to be very clear, right? Even if you don't remember this regular expression, this formula, you can simply do it. Arbitrary number of 1, this path, and arbitrary number of 0 and 1s. So the final string, the final regular expression is going to be 1 star 0, 0 star 1, 0 plus 1 star. So of course, just like when you were converting regular expression to NFA, that you created lots of unnecessary states, here definitely you can write down a simpler regular expression for this example as well. So this example basically shows all the binary strings that has the pattern 0, 1. So you can just write a simpler regular expression for this one as well. Something like, for example, 0, 1, and put the 0 plus 1 at the beginning of that and 0 plus 1 at the end of that. So this is going to be something similar to this. I know, at least more readable. Okay, another example. Here is, this one is just a little bit more complicated. Again, I have one starting state. I have 2 final state. So I can actually just consider each one separately and try to remove the intermediate states. Just, I will first try to remove Q1, then I will consider 2 different cases for this final state and this final state. Okay, so to remove this intermediate state, you should just preserve all the paths that go through this state, right? One path is going to be the one that go from Q0 to Q2. The other path is the one that go from Q2 to Q2 itself, right? So Q2 can go to Q1 and just come back to Q2. Nothing else, no other path needs to be preserved here. So if I remove Q1, I need to just add one path from Q0 to Q2. Let's just mark both of these as an accepting state. The path here is going to be one arbitrary number of zeros and 1. How about Q2? I had a 0 from previous, and then I need to get the union because Q2 can go to Q1, see arbitrary number of zeros, and come back to Q2. So this is going to be 1 arbitrary number of zeros and 1. So I removed Q1. Now I reach to this situation that I have two final states. I would first consider the case that Q2 is not a final state. Then I will consider the case that Q0 is not a final state. So if I marked Q2 as a non-final state, I didn't mean this is not final. Q2 is not final state, so the situation that I have is this one. What does this NFA is representing? This is going to just represent 0 star, right? Because there is no other path to reach to the final state that I have here. So this is going to be represented as 0 star. The other case is when I turned off Q0 and I only have Q2 as a final state. So the situation that I have is like this. Again, I can use that formula, but the simpler way is that the only path to reach from Q0 or Q to Q2 is arbitrary number of zeros. You need to see this one and then arbitrary number of this pattern, which is going to be this one. So I have a regular expression for this case. I have a regular expression for this case. Get the union of these two. This is going to be the final result that represent the this DFA. Let's just see another example. This one, again, I have two accepting states. So first, try to actually remove this intermediate state. I will just convert all of the transitions to regular expressions. So if you have more than one transition, then they are going to be union. Then remove Q1. By removing Q1, the only path that went through Q1 is from Q0 to Q2. So this one is going to be added, this path from Q0 to Q2. And I have two possibilities, Q2 as an accepting state and Q3 as an accepting state. Consider them separately. So if Q3 is an accepting state, I need to remove Q2, right? But Q2 was, an intermediate state. Remove it. The result is going to be this one. So this is the final NFA that I have. You can just convert it to a regular expression. The equivalent regular expression is going to be arbitrary 0 binary string, and then you need to put this one. Okay, the other case is that you consider Q3 to be a non-accepting. If Q3 was a non-accepting, you can just ignore it because it is after. It's not actually playing any role in reaching to Q2, right? So this is going to be the other case. Write down a regular expression for that. This is going to be the regular expression. Write arbitrary number of 0, 1, then this label. So this is one regular expression, this is one regular expression. Get the union of those two. This is going to be the complete regular expression. This one can be actually simplified more, but I'm going to leave it as is here. Here is another example. I can actually just leave it to you. I've written the full answer here for you that shows how to remove first Q4, then we remove Q3, then we remove Q2, and at the final you will actually reach to a state that the final state and accepting states are the same. So the regular expression for that is going to be whatever is the label, you just put the closure operator over that. Okay, there is one more example here that I'm going to just skip. You can read through it later. To just close this lecture, at the end I wanted to talk about some algebraic laws for regular expressions. These are going to be some rules that helps you to simplify your regular expression, or in fact understand the regular expressions better, because you have already seen that regular expressions can be very tricky, so you should be careful when you are working with them. So there, for a single language, you can write plenty of different regular expressions that looks very different. We have already seen some example about that. So these rules are going to help us to understand regular expression better. The first rule is commutative rule. You actually know that it is applicable over the union. The union of two sets, there is no order between them, right? So U, the set of strings represented by U, union the set of strings represented by V are going to be the same, right? So if I write as U plus V in the regular expression is going to be the same as V plus U. So it doesn't really matter if you write it 0 plus 1 or 1 plus 0. Both of these two regular expressions are representing the same set of strings. Okay. The other thing is, but actually just one thing, be careful. 0, 1, of course, is not equal to 1, 0. This concatenation is actually telling that the string starts with a 0, ends with a 1. This one starts with a 1, ends with a 0. So the concatenation, the rule, the order is important for concatenation. So be careful about that. The other rule is associative rule. So if you have the V union W and then get the union over U, okay, you can actually get the union of U and V and then get the union with W. So this is associative rule, the same for the concatenation. So when you are writing as U, V, W, you can just concatenate U and V first, or you can concatenate V and W first and then concatenate U before that. Just be careful that you cannot change the order of them. But it doesn't matter if you concatenate U to V first or V to W first, and then actually concatenate W to that, or concatenate U before this. The other rule is identity rule, that the union of any regular expression and the MT is going to be that regular expression. Also, the concatenation of epsilon and any regular expression it doesn't actually matter the order. This is the only case that the ordering, the concatenation doesn't matter. You can put epsilon before or after U, and it is at the end is going to be equal U. So kind of you can think of it as this is just like 0 in addition, that for example you have 1 plus 7 plus 0 in in algebraic, that we know that this is going to be equal to 7. So 0 is just like the empty set for us here. Or here epsilon is just like 1 in math, that you can actually multiply to any number and the result is going to be the same. This rule that we have already actually seen it again. If you concatenate empty set to any regular expression, the result is going to be empty. Okay, this is very important. Be careful about this one. So it's just like you are concatenating nothing to a set of strings. So if you are concatenating nothing, it's just remove everything, It's just like you are multiplying 0 to a number, right? It removes everything. It just makes it 0. Distributive, so if you concatenate U to the union of V and W, it's just like you concatenate U to all the strings in V, and then you concatenate U to all the strings in W and get the union over that. So the result is going to be the concatenation of U and V union the concatenation of U and W. Just like if you put the union before W, this is like again the concatenation of U and W union the concatenation of V and W. Idempotent, if you get the union of any set with itself, the result is going to be the same set. And these are some rules about the killing closure. That if you put the killing closure over the empty set, the result is going to be epsilon. Okay, remember? This was for any language. If you apply the killing closure over that, the result is going to be epsilon. So if you apply the killing closure over epsilon, again, this is going to be epsilon. If you apply the killing closure more than once over the same regular language, it doesn't matter. So R star 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 is not going to give you more. It's going to be equal to R star because already R star is covering all arbitrary number of R. Okay, so if you apply it more than once, it's not going to give you more. So this is just a notation again. So if you use the plus instead of a star, it's just like you have at least one repetition of the regular expression and then arbitrary number of that. Okay, so this is just like a notation again for us. This is again just a notation, just a definition. So it's just like this one is including epsilon, and again this one is a notation. If you probably have seen this notation in the regular expression of different languages, different, for example, in Java, or when you are writing the some rules in the Unix environments, in the command line of the Unix environment, this question mark, it's actually just representing that either epsilon or that regular expression U. Here are some tips again to simplify the rules. So these tips are very useful if you have two regular expression U and V and you are actually just concatenating them and get the killing closure over them, and you put the U after that. So it's just like you put the U before VU. So it is, using the rules you can actually prove that they are going to be equivalent. So it's just like you have UVU and it is repeating, so it doesn't matter if you take U out of the killing closure before or after the rule. But just be careful, this is not equivalent to this. Just think about it in this way. If you have 0, 1 killing closure, this is going to represent all these type of strings. Right? Just all arbitrary number of 0, 1s. But you cannot definitely write it as 0 star 1 star, because this one is going to represent all arbitrary number of zeros and then followed by arbitrary number of 1, right? So this one is going to represent this one, all of these strings, all of these strings. So of course this one is not equal to this one, so be careful about this rule. So if you have U star U, you can just write it as U star. If you are getting the union between these two, it's just like you can write it as U star, right? Because basically this one is going to be U plus and you are just you get the union with epsilon, so of course this is going to be the definition of U star. What else? If you get the union of epsilon and u, whatever is u, it doesn't matter what is the regular expression, if you put the killing closure over that, you can just simplify it and write it as killing closure over u. I mean, these two are the very nice thing, that if you put u star v and then killing closure over all of that and then put the u star at the end, it's just like you are saying arbitrary combination of u and v. So I can write it as u plus v killing closure. So it is the same as writing it in this way. It doesn't matter that if you put the u star before or after. So just think about it. Just think about the idea. You are allowing, by writing something like this, you are allowing arbitrary combination of u and v. So of course I can actually say that this is equivalent to this set of, to this regular expression. Here are some examples. Just try to actually check the truth value of following the statements. Is it true or false? I mean, is it equal to r star? I have actually discussed about this. Yes, it is, because you are just telling that arbitrary combination, arbitrary concatenation of r. And yes, putting a star over and over, just apply it more than once is not going to give you more. So this is going to be true. How about this one? Are they going to be equivalent? Of course not, because you can just think about it in this way. Whenever you get a question like this, try to simplify that. Just try to say that instead of r, I would put a simple expression like 0. And instead of s, I will put a simple expression like 1. Then try to see that this expression is going to be equivalent to this expression or not. If not, of course, the answer is false. For some example, they might be actually true, but in general, they are going to be false. So just like that, I can actually prove you that this is going to be false, because something like 0 plus 1 is going to give you arbitrary binary strings. Although 0 star plus 1 star is going to give you all strings which are only zeros, union with all strings which are only 1, arbitrary number of 1. Of course, they are not going to be equivalent. And how about this one? This one is just a little bit tricky, but again, if you put some 0 ones, or even actually simpler, when you see this closure over all the string here, all the regular expression here, it just tells you that, okay, epsilon is going to be represented by this regular expression. Can you represent epsilon using this regular expression? No, because in this regular expression, here it allows you to create a regular, epsilon. But here it's just you are forced to have a copy of r and a copy of s. So of course, again, this one is not going to be equivalent. This is going to be false. So how about this one? Are they going to be equivalent? Yes, they are. And the whole idea here is that you can think of it as this one is going to give you arbitrary combination of r and s. And again, this one is going to give you exactly arbitrary combination of r and s. Because so far, from this r star and s star, you can just say that, okay, definitely r star, s star is going to give me r, right? And r star, s star is also going to give me s. So this is going to give me r and s, and this is going to put the concatenation over all of them. So of course, this is going to be equivalent to all the combination of r and s. And here is, just showing some steps to prove, all of these combinations, that if you see them, they are going to all give you the same thing. All the combination of u and v. Here I have more examples for you, and I put actually a couple of more examples at the end. I just one can actually skip them through the video, go through them, and if you had any question, the solution for them is available here. Okay, I put all of the solutions step by step, but just if you had any question, we can talk about it during the office hours. Okay, so this lecture is covering chapter 3 of your textbook, so please try the exercises there as well. And if there is any question, we can talk about it during office hours.